Okay, well, I think we're a little bit after the hour now, and I think enough people have logged on. So let's go ahead and begin today's webinar on battery-based systems for lighting applications. Again, my name is Rob Rollo. I'm a senior engineer with Sunwise Power and Battery. And actually, I'm going to have a co-presenter today. I'm going to have Errol with us. Errol has a lot of good technical knowledge, and Errol is going to go ahead and handle some of the component portion of this presentation. So with that being said, a couple other things. If you have any questions, please use the questions box on the side panel to ask those questions, and we will address those as we go or at the end of today's webinar. Also, this webinar is being recorded and will be available on the Sunwise website within the next 24 hours. Just to let you know, Sunwise has over 20 years experience in off-grid systems. I myself have had over 25 years experience in the PV and off-grid power market. We do everything from standalone systems, hybrids, battery backup, and most any other systems to do with off-grid power. We have warehouses, sales offices, engineering offices around the country. And again, we have many markets we address, everything from hybrid systems, cyclocharge, standalone PV, UPS applications. We can do ISO 9001 and UL 508A when needed. Our systems are designed to IEEE standards. And some of the other services we can provide technical specification writing, we can do upfront design engineering, troubleshooting assistance, we can do trainings, say surveys and things like that. Okay, so today's webinar, we're going to break it up into a few parts. We're going to have off-grid lighting, and that's going to be a major focus. This is mostly PV based. We're also going to touch briefly on grid tied and battery backup. And the reason for that is that most lighting applications are not critical, so most are not going to require a UPS for that, but I will touch on that as we proceed here. So for the standalone, we could also have AC here too, but the little diagram is showing just DC. So generally you're going to have a solar module charging a battery through charge controller, and then the load's going to either be connected through the charge controller or through an inverter, depending upon whether it's AC or DC, and I'll talk about more of that as we proceed. On the grid tie side, we're mostly looking at an AC light, and you can have an inverter charger, or you can have a straight UPS system, which means the load is going to run off of the battery directly. There are advantages and disadvantages to both, and we will talk about that as we proceed. Okay, so this presentation is going to cover up to the lighting itself. We're not actually going to talk about the lights themselves. We're going to talk about the power for it and the control products. We're actually talking about the lights. So we're going to stop at the load output terminals of the system. Okay, and again, our focus is mostly going to be on the charge controllers and some of the features of those. I think you're going to be surprised at some of the features that these controllers have that you may not be aware of, and hopefully everybody will learn today something new that did not know about what some of these controllers are capable of doing. And maybe one of these features could help you in one of your applications. Again, the feature is not going to be on the lights themselves, but rather on the controls and the system powering them up. Okay, so we're going to first talk about some of the considerations to consider with these systems. We're going to talk about some of the various lighting applications. That's important because some of them are critical and some are non-critical, and how you handle them in terms of design it may be different. So we'll briefly touch on that. We're going to talk about grid tie systems first, and then we're going to talk about standalone sizing for the off-grid systems. And then we're going to go into the some of the features of the various lighting controllers, the solar power ones, and then also some of the specifics on specific models. So let's talk about some of the considerations. First, when it comes to the off-grid, you may want to refer back to our webinar last month on basic system sizing. We're going to refer to that a few times and not get into that in great detail in this webinar because we've already kind of covered that. We're going to try to focus on the lighting system itself on this and the lighting controls and features. So we'll probably refer you back to that webinar for specifics, but we will touch on that briefly. Also, with that being said, you want to treat the lighting load just like you would any other load, and we will get into that in more detail as well, some of the considerations for that, because the lighting loads are a little bit more complicated because of how they operate. So we're going to touch on that in a minute. Some of them may be AC or DC, so if they are DC inverters required, and I'm going to talk about that in the considerations in one of the next slides as well. So generally, if you're in an off-grid application, trying to use a DC light is the most efficient option. We're going to talk about why that is in a minute. So if you can use a DC lamp or light, that is the best possible option. Most of the lighting loads are actually going to be intermittent, generally nighttime only. However, there are some that are going to be daytime, perhaps when it comes to some type of navigational load, or I know for obstruction lighting, sometimes it might have a white light for the day and red lights at night, or vice versa, or something like that. So sometimes there are different size loads for day and night, and some loads are nighttime only, especially when it comes to street lighting and security lighting and stuff like that. So keep that in mind when you're doing your load calculations. And you might want to think about and consider, okay, with these loads, how much is going to be nighttime, how much is going to be daytime, and you're going to have to do a little bit of math there to figure out your total combined loads if you do have daytime and nighttime ones. Also, generally, something else to consider is that generally lighting loads most of the controllers do have a low voltage disconnect feature of them, which basically means if you have depleted the batteries too far, it will disconnect the load to protect the battery. This is important in critical loads. If you have a non-critical load, you may not care, and you may go, that's fine. It's okay if the light goes out at 4 o'clock in the morning, nobody may care. But if you're on obstruction light or navigational type of beacons or something like that, you may want to make certain that those operate all the time. So you may make certain that you oversize the system to compensate for that. We'll touch on that a little bit more when we talk about the basic system sizing, because in the basic system sizing, we do go through critical and non-critical loads. Okay, getting back to the AC nature again, if you are going to have an AC light, make certain you include the inverter inefficiencies in the losses design. Most inverters are somewhere around 85 to 90% efficient, so you need to add an extra 10 or 15% to the load to compensate for that inefficiency. Also, this is another big one. If you have strictly a nighttime powered load, that the lights strictly come on at night and not during the day, the inverters actually consume 3 watts to 8 watts, depending upon the inverter model, just sitting there idle in standby mode, even in what they call no load mode or standby mode, just to keep the circuit boards powered up, are generally between 3 and 8 watts. And that can be a big load. If your light is only maybe 12 or 15 watts, all of a sudden having a 3 to 8 watt inverter on there can be a huge load to your system and can increase the size of your system by approximately 20%, 25%. That's a lot of extra money they have to spend. So again, trying to use a DC light, as you can tell, is going to be your most cost-effective solution. Even if the light's a little bit more than the AC one, by the time you factor in these inefficiencies and the cost of the inverter and stuff, that the DC light may be a more cost-effective option. One other thing to consider is, I know everybody's big on LED lights, but LED lights are not always the most efficient option. And I know some people might be surprised to hear me say that, but I've gone through that sometimes before. Fluorescent lights can be just as good in most applications. They can be just as efficient and produce just as good a light quality or better. Sometimes it's not the technology of the light that's important, but it's the amount of lumens it's going to throw off. And again, the lumens is the amount of light, and that's important that be in the visible light spectrum. I bring that up because in the early days of doing this, they used to use what they call low pressure sodium lights. You still might see the sodium lights around nowadays. If you see a light that's kind of yellowish in color, very yellow, those are sodium lights. And the problem with those yellow colors are they're in a light spectrum that's not very good to the eye. So although they may throw off a lot of lumens, it's not any light spectrum that's visible to you or in a good quality light spectrum. So sometimes it's not necessarily the light itself, but it's how many lumens is it producing? Is it producing the lumens in a visible light spectrum that's good to you? And those are things we want to look for. And again, is it omnidirectional or just directional? And again, this may depend on the application. If you're doing some type of Navigational lights, you might want that to be omnidirectional. However, if you're doing some type of street lighting, you might want that to be directional, just straight down. You may not need it to go in all directions. And a lot of stuff can be done based upon optics and reflectors. So sometimes the optics and reflectors can be more important than the light itself, because this is how that light is disseminated for omnidirectional, or for directional, the reflector is how it reflects that light out. So if you have good reflectors and optics, you can sometimes get away with a less wattage light, which means it doesn't really matter whether it's LED or fluorescent or other technology. Again, it's more about trying to get that light where you need it and the quality of color that you need it to be in. So let's briefly discuss some of the applications for these lightings. And again, this is important because if it's a non-critical application, if the system fails, you may not care as much. But if it's critical, you might. So generally, so these are generally considered non-critical. And that's security lighting. That could be a walkway, a parking lot, things like that. Sports lighting, these are signs. They could be scoreboards and things like that. Then you have just general signs, which are billboards, businesses, HOAs. You might have some residential area lighting, patios, landscapes, things like that. Construction lighting for construction zones, either floodlights, again, those might be directional, or just area lights, omnidirectional. You might have some recreational, outdoor parks, structures, kiosks. I was referred to a lot of those. That reminds me of Park Services purchase a lot of lighting for what they call comfort stations out in the parks, basically restroom areas. They'll use lights on those, both inside the bathrooms and outside, so that people can spot them easily. So that's another one for those. Some of the critical applications, we already mentioned this a few times already, would be obstruction lighting. These are for towers. Towers can be anything from a telecommunications tower to utility towers to wind machines. We mentioned navigation a couple of times. Again, these can be buoys, markers. It could be airport lighting. And again, most of these are considered critical. Traffic flashers. These can be school zones, crosswalks. They could be also for fire stations. Another one also is dangerous curves. A lot of those are for dangerous curves as well, and things like that, or other type of possible obstruction. I'm thinking sometimes in northern areas you might see flashers that come on for winter storm, for icy road conditions, things like that. So they could just be a caution hazard type of sign for traffic. And then of course your traffic lighting as well. Okay, I'm just going to briefly cover some of the grid tie stuff now. And again, this is where the utility is going into a inverter charger, and then going to battery. And similar to a PV system, for the standalone, you need to understand your loads, its values and voltages. And this is especially important when it comes to battery autonomy. So you're going to actually handle this in some regards the same as you would a standalone PV system for the initial part of it in terms of the battery sizing and for understanding the loads. The only thing a little different here is that you might want to understand your recharge times with these systems. And then also the charger features, and whether it's a true UPS or switching. If you have ones with a transfer switch in them, there's a switching delay on those, and those may or may not be a problem, and I will talk about that a little bit more in detail. So basically you're going to have that switching delay with an inverter charger type of setup, and basically this is going to mostly apply to AC loads, because obviously a DC load is going to be connected directly to the battery. But with an AC load, the inverter charger can provide current to charge the battery, and then also AC power directly to the load. And then what happens is it has an automatic transfer switch in there, such that when it loses utility power, it will transfer from the utility to the internal inverter itself, to what they call invert mode. The problem with that is there can be a slight lag or delay, and that may cause the light to blip. That may or may not be a problem. If you have sophisticated controls in the lighting, that may take time to reboot, may be a problem, especially in a critical load situation when it comes to obstruction lighting and tower lighting and stuff like that. You may not, if you have an airplane up in the air, having it down for 10, 15, 20 seconds while it reboots itself may not be a good thing. So you may want to keep that in mind. Obviously, if you have other type of lighting controls that may not be an issue. Hey, it can be down for 5-10 seconds, nobody cares. But just keep in mind that there can be a switching delay that may be a problem with those applications. So in a true UPS, what will happen is that you basically have a straight up charger. So the charger charges the battery, and then the battery then powers up the inverter. So you literally have two separate components. You have a separate battery charger and a separate inverter. What this means then is since the inverter is always running off the battery, it doesn't really matter what happens on the AC side. That inverter is always powering up that load, and there is no switch delay. This can be a problem with this can be a problem with any UPS system, not just lighting in particular, with any UPS systems. And I know that's a problem for some loads, that they see that blip for that transfer. It causes their stuff to reboot, which was kind of the whole point to have the UPS. So just something to keep in mind. Some inverter chargers can have a very high switch rate, which means that they can be like a half a cycle or so, and some of the loads can handle that. Some may be longer than that. There may be 2 or 3 cycles for the switch delay, and that may be enough to cause the loads to reset. So again, you just need to know your loads and whether it's critical or not, and whether that delay is going to be an issue or not. Okay, so for sizing the grid tie for UPS type application, and again, this will be the same for the standalone solar. You're going to do it the same way because you're dealing with batteries. So whenever you're dealing with batteries, you're always working at amps and amp hours. So you're going to convert your load to amps. Okay, and that's going to be at the nominal battery voltage. If you have an inverter in there, you need to go through the process of including those inefficiencies and those equations and stuff like that. So you want to take that into account. Okay, and then you want to multiply that by the number of hours of backup time, and this will give you amp hours. Okay, and then you're going to want to divide that by the depth of discharge. As you mentioned, there's usually a low voltage disconnect in these. You want to protect the batteries from being over discharged. For most batteries, that's going to be at the 80% point. So you're going to only use about 80% of the batteries. You're going to take the amp hours that you just calculated. So again, that's the load times the number of hours of backup time you want. You can divide that by 80%. That's going to give you your desired battery capacity that's required. Now, what that does not include is any other derates you might want. Temperature is an important one. If you're in a colder climate, you may want to add a temperature derate to that. In most cold climates, it's not unusual to use an additional 20% derate for that. So you may want to divide those batteries, whatever that capacity is, divide by additional 80% again for some temperature derates. But I would refer you to the battery manufacturer's temperature derate curves for that. So you would need to know the temperature in your area, and then look at those derate curves, and then apply whatever derate factor you wanted to for those. Okay, now the recharge time. This is actually dependent upon whether you have a true UPS or inverter charger situation. For the reason is for the UPS, the battery charger needs to support the load and recharge the battery at the same time. Remember, everything is going through the battery, so all power has to come off that battery and charger. Whereas with the inverter charger, because of that transfer switch, it can then divert the AC to the load, so then the full charge it has, the full DC current, can then go to recharging the battery. Okay, so for the inverter charger, you can simply divide the battery capacity, and that is to the depth of discharge required. Again, since your LVD is going to be at, say, the 80% discharge point, you only need to worry about 80% of the battery capacity. So you can simply divide that by the charge current from the charger, and that gives you a pretty good approximation of your recharge time. Now, if all you have is a battery charger, then you need to subtract from that charger output first the load current, because remember, you need to support the load. So if you have, say, a 25 amp charger as an example, and your load is 5 amps, then you only have 20 amps remaining to recharge the battery. So then you would take whatever that remaining is, and then divide the battery capacity by that to get your recharge time. So I think that's the big key there is that a lot of people forget about that. They're thinking, oh, I have a 25 amp charger, I can charge my battery at 25 amps. You can't, because remember, part of that has to go to support the load first, then the remainder needs to go to the battery. So if you have, and that's why something to think about when you're sizing your charger, or that you should think about considering when sizing a charger. If you have maybe a larger load, like a 20 amp load, and you have a 25 amp charger, then only 5 amps can go to recharging the battery. and that might take a lot longer. It may take more than 24 hours to recharge your battery, and that may not be acceptable to you. You may want to have the battery charged in 8 to 12 hours, so you may want to go to a bigger battery charger because of that. Now, if you're okay with taking 24 to 40 hours or more to recharge your battery, then that may be just fine. So it's just something else to consider as you're selecting your components and looking at the capacities of the battery and the current of the charger that you have. Okay, so let's talk about the standalone PV system. And again, this is where the solar, the sunlight is the only charging source. We're not going to have any type of extra utility power there. We're not going to talk about a generator or wind or anything else. We're just going to look at strictly the solar. And as I mentioned before, we're going to refer back to our webinar that we did last month on the basic system sizing. And so again, there are 5 steps to that. The first one, of course, is identify the sun hours at the site you're at. Then you want to calculate or make an estimate of your system losses. And then you're going to calculate the load. Same thing in amp hours a day, same exact thing we just did for the UPS. Again, the load calculations in those are exactly the same. Then you can go ahead and size the array and the battery. So and here's just kind of again, just a general map of the sunlight conditions. And again, this is the worst month average. And again, I refer you back to our webinar on that last month on basic system sizing. The system losses are expressed in a percentage, typical or somewhere between 10 and 20%. And again, these losses are dust, battery inefficiencies, parasitic losses of charge controllers, inverters, if not included in your load calculations for that, things like that. Okay, so just a quick example here. If we're going to take a 15-watt load at 12 volts, we're going to go ahead and have a light that's going to be on all the time. It could be a obstruction light or something like that, or a navigational light. So, so we take that 15 watts divided by the 12 volts. We're going to multiply by 24 hours. That's going to give us a load of 30 amp hours a day. And then we're going to go ahead and use the non-critical, which is an array to load ratio of about 1.2. And we're going to go ahead and use a 140 watt module, which is about 7.8 amps. And if you go through all the calculations, it basically says you need 1.7 modules. And because you can't do a 0.7 of a module, we need to round up to the nearest whole number, which would be 2. So this system will require 240 watt modules to support a 15 watt continuous load at 12 volts. Battery calculations are similar. Again, since we're talking about a non-critical load, we would use the 5 days for battery autonomy. If this was critical, we would have used a higher number of about 7 days, or an array to load ratio an array to load ratio of about 1.3 to 1.4. And again, I refer you back to the system sizing webinar for that information. So we come up with a required battery capacity of about 187 amp hours. So that would be either one 8D battery or a couple of the group 27 batteries in parallel. So to summarize that, again, you would identify your sun hours at the site. In this case, it was 3. System losses, we assumed 10%. We calculated the load to be 30 amp hours, and that gave us an array of 240 watt modules, or 280 watts total, and a minimum battery size of 187 amp hours. So I'm going to turn it over to Errol from here. Errol's going to go through some of the features and functions of these solar lighting controllers. These lighting controllers have got special features in them specifically designed for lighting applications. So I'm going to let Errol talk about those in more detail now.
Thanks, Rob. Appreciate it. If at any point I miss anything, or if you want to interject, just go ahead and speak up and go ahead and mention anything else. So as Rob mentioned, most of the solar lighting charge controllers can perform basically multiple functions at once. It can act as both a solar charge controller and a lighting load controller simultaneously. And so within these units, there exists a pretty wide range of functionality and features specifically designed to control lighting loads. So some of those include lighting timers, which can be either customizable or preset from the factory, dawn and dusk sensors, which utilize the solar array to tell the system when the sun is rising and setting. Light sensitivity, which can be used to control the light threshold levels at which various lighting functions are triggered. This can be caused by things like light pollution and specific module selection and other things. Some lights have built-in LED drivers, so they basically have built-in power capabilities to power LED lights at various power ratings, and we'll cover some of that. Some charge controllers have single load and dual load capabilities so that they can run multiple loads simultaneously off of one controller. Some units have dimming capabilities, which allow the unit to vary the power given to the lighting load depending on the health of the battery system. And then we have motion sensing and things like memory and learning control. And we're going to go over most of these in relation to a handful of products. So this list is by no means exhaustive. This is just basically a selection of a handful of products that we're at least somewhat familiar either working with or having a relationship with the manufacturer. So just going over some of the things that we're going to mention and talk about. From Midnight Solar, we have both the Brat and the KID charge controllers. The Brat is a PWM and the KID is an MPPT. From Morningstar, we have the Sunlight and the Prostar Gen 3 PWMs, as well as the Tristar. And then we also have the Sunsaver MPPT and the Prostar Gen 3 MPPT. From Focus, we have the CIS, CIS-N, CIS-N LED, and CIS-MPPT. And then from Seca, we have the Solarix line, the PR line, Solsum line, and Tarum line. And as I mentioned, even this list is not complete for just these select manufacturers, but every charge controller there has some degree of lighting functionality. So we're going to go over a little bit of that. So as I mentioned, the purpose of the lighting / charge controller, because in most cases, but not all, they are the same unit. The purpose is to control the times and specifics of how and when a lighting load will turn on or off. So we're going to go through a bunch of different examples of how that may be. The solar array, as I mentioned, takes the voltage from the light levels and passes that information to the charge controller in order to tell the system when sunrise and sunset happens. Now, the complexity of the lighting controls on these units ranges from dial select, where you'll basically have between anywhere from 10 or 16 or 12 or less rotary dial selections right on the charge controller, and you'll have a simple table that tells you what the factory presets are for each one of those lighting modes, and you'll get a feel for that. And then we move sort of up in scale to some level of lighting programming capability to set timers and set points for length of duration between various turn-off and turn-off phases. And then we sort of continue to scale up towards custom and full programming capabilities, and then eventually moving into software with user interface that can be programmed on a PC and ultimately sent to the controller. All right. So this is a table that we've come up with that goes over some of the feature comparisons between a handful of the charge controller lines that we want to discuss. Now, note that we have put in a disclaimer at the bottom on accuracy. Ultimately, we encourage folks, if they have questions, to reach out to the manufacturer themselves, or they can be more than welcome to route those questions through us, and we will get a response direct if we can't answer it clearly. So just kind of briefly going over some of the options here, you can see we've basically broken out the left hand of the table into the specific features we want to cover, some of them. That includes preset factory lighting timers from the factory that can be set either on a rotary switch or via dip switch settings. The capability to sense dawn and dusk through the solar array. Things like a lighting test button in order to be able to verify whether or not the lighting programming and the lighting load is set up correctly. Usually those happen in a 5-minute push button interval, as well as a lot of the other functions that we talked about, LED drivers, dual load, dimming, motion sensing, and sensitivity control. So as we go through this, if folks have any questions, feel free to reach out in the chat window, or you know, we can return back to this if anybody wants to revisit this as we go through. So this gives a very simple wiring diagram of a lighting system with a solar charge controller, a battery, and a solar array. And this is courtesy of Midnight Solar, straight out of some of their product media. So if you basically ignore all of the single line diagrams, you'll see in the bottom right we have our battery bank. In the top right we've got our solar charge controller, and in our top left we have our solar array. Those are basically the three primary components that we've been discussing and that are of most concern. Everything else is mostly just circuit protection, grounding, and combining. So usually we boil all that down into a simple control panel, so I don't need to get worried on that. So starting off with the Midnight Brat charge controller, this is a relatively simple rotary select with up to 16 lighting and load control options. You can see that there's also the load test button on the bottom left-hand side, as well as most of the details are printed right on the circuit board to make it very clear and easy. So briefly going through what some of these preset timers are and how they function, you'll see that we basically have 9 modes for lighting starting at dusk, and then a few other modes for combinations of early night and early morning lighting. So for instance, you could set the lights on for either 3, 4, or 6 hours after dusk, and then control when they turn off for a certain period of time before dawn, either 1, 2, or 2 hours. The lighting starting at dusk typically will turn on at dusk and then just remain on continuously until dawn. So basically a night light function, where as soon as it senses that it's dark out, powers on the lighting load and then turns off when it gets light out again. So moving on to the KID, also for Midnight, which is an MPPT controller. And note that these units have many, many other functions and features that we're not discussing. We're just focusing strictly on the lighting aspect. You'll see that this is done via the programmable interface on the menu. So basically you would go in and control it through one of 3 ways. Either a night light, which is just basically a dedicated night function, a daylight, dedicated day function, or dusk plus a programmable amount of hours, which is basically the light turns on when dusk happens and evening sets on, and you control how many hours the light stays on until it shuts off. Okay. So going on to the sunlight charge controller from Morningstar. This is, again, a rotary selectable charge controller. You see we've basically got about 8 or 9 options here, and we can control basically always on during the evening, dusk to dawn mode, which you'll see is one of the most common presets that you'll have. And then again, basically preset controls for the amount of time after dusk and before sunrise. And then you'll see for other units as you move up in complexity, the general rules or the general programming structure is more or less the same. You have these dawn and dusk set points, and then you can basically control through custom programming the amount of time before and after each one of those events the lighting is triggered. So basically you could have it come on a certain amount of time before dusk even, and so we'll get into that as the complexity goes on. But for some of these, you basically have a set number of presets from the factory, you select which one you want, and then it should work automatically. So again, this has a test button on the bottom right-hand side, which basically for 5 minutes will show you the lighting load so that you can make sure everything is working correctly. The timer accuracy is on the order of a couple seconds, so it should be relatively accurate if any sort of precision is actually required. Again, detects day and night through the PV array, and then this one has 10 options, 12 and 24 volt. All right, so moving on up in complexity, also from Morningstar, we have the new Gen 3 Prostar line, and this includes both the Prostar PWM and the Prostar MPPT. The PWM shown on the left and the MPPT shown on the right, both with the meter. So the way that this works, as I was mentioning, is a programmable control done through the meter right on the unit. It's also possible to connect via RS-232 and program on the PC via MSView and other the desktop software from Morningstar. Basically, the top line bar is shown for the on state, and the low line bar is for the off state. And it basically has clear markers for daytime and nighttime. And so basically, as I mentioned, you set the exact time that you want around the dawn and dusk points, either before or after. And the Prostar comes with up to 4 timing controls. In the handouts, you'll see that we've included a document for the meter map of the Prostar Gen 3. If anybody is interested, and that's of course available off the Morningstar website, you can see a lot of the details for the exact structure in the meter menu to go through that. Okay. So the interesting thing is that Prostar Gen 3 PWM and the Prostar MPPT both contain the same lighting control functionality. Really, the brains of the unit behind the scenes are really the exact same. And so from a lighting control standpoint, both those units are equivalent. One thing that we want to mention about them, which is a really nice feature, is the lighting sensitivity control. They refer to it as the sunrise sunset threshold. And this is important primarily because of lighting pollution issues. If you're in a city that has very high light levels, it can obviously be drastically different than if you're in a remote place, so much so that it can cause issues and be confusing for these charge controllers. They have the ability to program around that, which is a very helpful thing. All right. Can we get next slide, Rob?
Yeah, Errol, are you not seeing that?
Oh yeah, I'm not. Um,
How about that one?
no, I'm not. I wonder if I need to reconnect. Oh, I see it now. Sorry, that was a delay. Can you go back to the first Tristar? All right. So the next unit we want to talk about is the Tristar unit. Again, this has programmable control and preset set points from the factory. All right, next slide, Rob. The preset, the set points from the factory are controlled via dip switches rather than via a rotary control. So note that basically we have the same general layout structure for hours after sunset and hours before sunrise, controlled through 6 dip switch settings. And then we also have the all-night feature, the dawn to dusk mode. And then we have the last one, which is user-defined program, and that's done via either the meter add-on or via an RS-232 cable to a PC via the MSU software. Okay. We also, I forgot to mention, we also have lighting control setup document published by Morningstar that goes over some of the functionality for the Tristar unit. That's both as an attachment and with a link. Okay. All right, so the next one we're going to talk about, the next unit that we're going to talk about is the Tarom series from Steka. And this is an advanced MPPT controller with quite a bit of lighting programming capability. Thanks, Rob. So one thing, the first function that it has is a morning light function. So basically what this will do is it will switch on the load a certain amount of time before dawn. So you'll note this is actually for some fairly specific applications, but if you wanted to run a heater or a feeding system or bus stop lighting for a certain amount on just the morning, it has that basically early dawn programming capability. Now, the nice thing about this is that there's actually memory behind these units in terms of remembering the shift from seasons and other things. So once you run this a single time, it will use that morning information to then be able to execute the programming. It needs to go through, as you see in the note here, at least one cycle. But after it goes through that single cycle, then it will continually adjust the time of dawn to account for, like I said, annual changes to the length of day, weather, and other details like that. Okay. So you'll see here the next function that it has is an evening light function. So this basically you're able to control all the parameters shown on the bottom. So you'll have the dusk event, and then in 5 you'll have the switch on delay, which you can control an amount of time that it delays the light to come on after dusk. Perhaps you don't want the light to come on for 2 hours afterwards. Then you can set the switch on time, that's the number 2. And then you control the load switch on duration, which is number 6. You can see from the contactor icon above that the switch is closed and the load is on. And then 3, you basically have your switch off time, and then 4, you have your dawn. So again, that same sort of general structure, formatting your program control times and logic around the dawn and dusk. So if we go to the next one, you'll see that we have basically a full nightlight function, which is basically similar to the last one, where we have the switch on delay as well as the switch on duration, but now we actually have a switch off delay. So we can actually control the switch off time by a specific amount related to dawn. So that will, of course, switch over time as dawn shifts. Okay? So between the automatic evening, nightlight, and daylight function, the configurations basically allow for most mix and match combinations of lighting loads that you would need. In addition to the functionality and control through these modes, there's an additional 4 custom lighting timers that we're going to cover in a sec, which allows you to set additional events purely based on custom timing programming. All right, so next slide. So as I mentioned, these 4 freely programmable timers can be set individually based on the day of week, as well as other things like start and finish time. So that allows you to run a schedule not just on a daily level, but within the days of a week resolution. Okay, next slide. So this is a screenshot out of the Tarot manual to give you a feeling of what the timer menu structure looks like. Most of these meter-based charge controllers will have a similar meter map menu structure. Some of the manufacturers publish those. We have it for both the Prostar Gen 3 and the Midnight Solar Kid MPPT attached on this webinar, but there may be others available. So as you can see on the left, you could set something for Monday, Tuesday, Wednesday, Thursday, Friday, but leave it off for Saturday, Sunday. Okay, next slide. The next ones we want to talk about are the FOCO CIS-N. In addition to basically all the other functions that we've talked about so far, these have a few additional ones that we'll cover, like dimming and motion control. Okay, next slide. This is another graphical representation of these light on, light off control structures that different manufacturers have slightly different takes on it, but really it's very analogous in that you have an hours after dusk, potentially hours before dawn. One interesting feature that they actually have is they have a middle of the night feature, which is another set point that can be used to tweak the lighting a little bit more precisely. So now, rather than just basing your delays or your timers around dawn or dusk, you can now actually do that around the middle of the night. Okay. So this slide is interesting. This does a good job of representing what we're calling this sensitivity effect, this lighting sensitivity. They call it their threshold setting range, analogous to the Morningstar Sunrise Sunset threshold. So again, what this allows you to do, if you want to go to the next slide, Rob, just so that we can highlight it, it allows you to basically take the voltage range that the solar charge controller is using from the array to trigger these dawn or potentially dusk events, and basically customizing that to be specific to your application. The light pollution is one of the major ones, but also the module that you're using can be affected. The max voltage of modules has continued to increase over time. As performance and module efficiency increases, we've kind of gone from 17 to 18 to 19 volts. And so that can be a consideration with some older charge controller units. If you're using a new higher powered module in combination with the environmental effects of the lighting, it may be necessary to program the sensitivity in order to get the lighting controller to actually trigger at the right time that you want it to. Okay. We're going to talk a little bit about the LED series. You can go to the next slide. This actually has power output capabilities for 5 to 15 LEDs in series and 10 to 15 LEDs for 24 volts. You'll see that they come in output ranges of 350 milliamp, 600 milliamp, all the way up to 2800 milliamp. And there are timers built inside to be able to control the LED brightness as well. Next slide. So just kind of showing you here, you basically have your output voltage ranges up to 49 volts in both cases. You have your nominal output current per string for your LED driver, and then it basically gives you a reference for your max load power in each case. Okay. So the last feature we wanted to talk about briefly, which is one of the more subtle ones, but also one of a pretty cool one, is to basically have motion detection capability to trigger any number of loads, often a lighting one, but it could be security-based. It could be really any load. but to basically have that motion detection sensor built into the unit and be able to program and trigger events around that is a nice functionality that a lot of people might not know exists. Okay, next slide. All right, and kind of to end things, I'm not really going to go into a tremendous amount of detail, but if there's questions or if people are curious, I encourage them to reach out to either us or Focus directly. But they have a software platform, Syscom, that's a standalone PC software. It can be used to connect to a variety, I think every CIS Focus charge controller. They've got an infrared accessory that they use to do the programming and the delivery, which is pretty cool. But this is sort of at or near the top of the complexity level for lighting controls. You have a standalone software with a full user interface and a lot of detail in order to be able to control a wider range of lighting functionality and controls. At least everything that we've discussed and probably much more. We're not experts in this software, but we did want to give people a preview for this and a feeling for it. And so if people would like to know more, feel free to reach out. Rob, if you want to go to the next slide, we've got a full screen just so people can get a feeling for just some of the settings and options that we have. All right, and then we've got some tech note sections, and you'll find the posting of this webinar after it's done, as well as all of our last webinars. And then we've also got a separate section for some past engineering bulletins with lots of detailed information.
And I want to highlight one other feature that we really didn't cover too much because we're talking specifically about lighting control, but if you notice as we're going through these controllers, some of them had features that also worked around daytime and nighttime. So you could actually program these for daytime load. You know, if you only wanted a kiosk to operate, you know, from you know, an hour or two after you know, sunrise to sunset or something like that, you could do that. I don't know, perhaps at a park or something like that, or some other kiosk. So if you want stuff to operate for daytime use only, you'll notice that there are several of these charge controllers with the more sophisticated features that allows you to program it for just daytime use. So just something else to consider. Again, I know we're focusing on lighting control, but just even any type of perhaps time of day control can be done with some of these units.
Thanks, Rob. That's good. So I will take the opportunity. We still have a few minutes left. We're more than happy to stay a few minutes later. Are there any questions from anybody? Feel free to put them into the chat window, and we'll go ahead and answer them directly if there are any. You might do the poll also, Rob, while we still have a few people here, just to get a feel for it.
Oh yeah, just out of curiosity, poll question is, how do you frequently use your lighting controls? Oh, we're still got it for about 50% now. It's interesting. It's kind of jumping all over the place. It's gone from at one point preset was higher, then advanced was higher, and now then at one point it was even, and now it's looking actually fairly even again. Yeah, it looks like 61% of it. Okay, I think it's probably over 60% have voted. So let's go ahead and share that information. Yeah, so it looks like it's all across the board. We have people that are about 30% are using the presets, and then 30, 35, or 36 are using the simple programming and the advanced ones. So it looks like it's all across the board for the most part.
Interesting.
Yeah, it is interesting. I would have thought the simple presets would have been more commonly used, but apparently not. Apparently, people are using a lot of these advanced controls. So hopefully, maybe some individuals learned about some additional advanced controls and features they may not have been aware of that were available out there.
Yep. All right. Well, if there's no questions, then thank you everybody for the time and for attending. Again, this will be posted on the webinar section of our website by the end of today, and we'll get notifications out for folks on that as well. And if there are any final questions, don't hesitate to reach out. More than happy to help.
Thank you all.
Thanks, everybody.